brings me to an important point. Nearsightedness is qualitatively more, I'm going to say, powerful for metals than for initiators. And here I'm looking at the effect of putting a finite barrier around a subsystem. The nearsightedness for metals has, phenomena that I discuss here within this context of nearsightedness, in the case of metals, have been studied long before. There is the biohydric theory, well known to chemists, electrochemists particularly. There are the Friedel oscillations, well known to people who study isolated impurities in metals. So here's some of the mathematics. Let's start with just mentioning insulators, and you'll see that you get by insulator here I mean any kind of system, even a molecule, that has a substantial gap between the ground state and the first excited state. That's true of such a gap between the many-body ground state of an insulator. You want to excite an electron and take it over a finite gap, so a finite many-body gap in insulators or in molecules. And I use either the terminology insulator or finite gap system as meaning referring to the same thing. Let's see, Nicola, can you give me the next one? And then I think there's only one more. In fact, give me the next one right away. Okay, here are some numbers. If you have a perturbation in an insulator, go back to the first diagram where I showed you this point R0 surrounded by a sphere, and you ask, let's turn the question around a little bit, when you make if the density change that you can tolerate is delta n, how big do you have to make the radius? How far away from that point do you have to keep the perturbation? There you have a rough description. It changes very slowly with the tolerated change of n, logarithmically. And you see there is a And that, in fact, has something to do with the structure of the insulating wave functions in the complex K-plane. This Q effective in the complex K-plane, there are certain branch points. At those branch points, one band is connected to the next, and the Q effective is the magnitude of the K, of the imaginary part of the K at the branch points. So you see this idea of looking at the wave functions as functions of complex wave numbers has some very interesting physical uses. For metals, you can see there's a different behavior in 2 dimensions, in 3 dimensions, but differing really only in the numbers, but not in the general form. So all these formulas give you some quantitative idea of nearsightedness. And there may be one more. Yes, this is this linear scaling method, and the person that has been most involved there is Yang, the co-author of the book by Parr and Yang, that many of you will know. And he calls this approach, and it was a very good literary idea, to divide and conquer. That is a good idea. It does omit the 2 things that I've mentioned. I will start with the quantitatively smaller one. It does omit the van der Waals interactions that penetrate any separation, any physical separation between these different parts of the system into which the divide and conquer technique separates them. And the other one is, as I already mentioned, long-range Coulomb interactions that also you put walls between your compartments and the divide and conquer techniques. They don't stop those interactions, and they connect the parts. And therefore, to a considerable extent or to a small extent, that will depend on the system, they thwart the linear scaling. I think that's it, but let's see, let's just check once more. Yes, go on, please. Doesn't go wrong. That's it, huh? Okay, so I hope I have stimulated your ganglia a little bit. There is lots more work to be done here, and I see a lot of energetic young people, and I would love nothing more than to see some of you push this kind of work further in the future. I think there are some interesting ideas, important and interesting ideas still to be developed. Thank you. So, questions?
Are there questions? Comments? Don't be shy.
There's one here.
Okay.
to realize this experimentally? That is one question. Other question is, when this system perturbed and nearsightedness effect is observed, what special feature or signature would this system manifest? So one is how to realize it experimentally, and second is what real or significant signature they would manifest when this effect is really picked up or probed by experiment.
Okay, I'd like to give you 2 or 3 concrete examples. Take a solid, a cube, if you will, with surfaces. The electronic structure just inside the surface is obviously not exactly the same as deep in the interior. So take the following viewpoint. Here's that point R naught that you're interested in. And let's say this is a perfectly crystalline material, except it is terminated by surface. So take the R naught inside and move it along towards the surface. As you pass through corresponding points, since this is a periodic lattice, you come to the same properties again and again. Let's say it's the center of the unit cell, then you go to the center of the next unit cell, looks just the same. When you come close to the surface, and you can measure this by nuclear magnetic resonance, for example, NMR. That's been done. It was one of the first things that we used. We used, in fact, stimulated much of this work. This work done at Bell Telephone Laboratories of this kind. I'll say a little more about that later. Let me finish. So as you look at nuclei nearer and nearer the surface, you begin to see deviations from the NMR frequency that you got for a nucleus in bulk. But you find that, let's say you want, you're willing to tolerate a delta N of 1%. And it turns out, now go back from the surface towards the interior, after you've gone through typically 3 or 4 planes, you already have within some percent, 2%, the same result as deep in the interior. So the nearsightedness range there is a few layers, and the measurement I've mentioned. So it is a very realistic thing, and a significant thing. Let's see, I'm trying to remember that old paper, very old, the NMR paper. Yes, I recall now what that was. This, I think the name of that person was Roland, and he worked at Bell Telephone Laboratories. He looked at an alloy, a fairly dilute alloy of zinc in copper. Zinc is highly soluble in copper. Maybe even completely miscible. Could be completely miscible. So he measured the copper nucleus has a quadruple resonance. That's a property of the nucleus. Okay? And he took, well, it's not exactly what he did, but let's say he took perfectly pure copper And then he got a sharp resonance because every copper nucleus was equivalent to every other copper. Now he put a small concentration of zinc impurity. Then most of the copper nuclei were still far enough from the zincs. The zincs are very dilute, okay? And so he got the same resonance as for quote-unquote perfect copper, perfectly pure copper. But as he increased the concentration of zinc, then he got still a very strong resonance at the same as for perfectly pure copper. And then he got resonances, additional resonances at particular shifted frequencies. And eventually this could be interpreted as the resonance, one of them, the most shifted one, was due to copper nuclei that were directly adjacent to the zinc nuclei. The slightly less shifted one came from copper nuclei adjacent to the second shell of acid, and so on. So you could, in this way, determine the effect of a zinc impurity on nearest neighbors, next nearest neighbors, and so on. You saw the nearsightedness. Okay? So there are many examples. Okay?
Does it have any benefit from the application point of view? If you create a material with nearsightedness effects, a small material, as you said, buckyball, can one get extra benefit out of it?
You mean
application-oriented benefit?
Yes, absolutely. Well, the last example that I gave was an example of an alloy. Well, you, for example, when you look at the intensities of these different lines, the most shifted line, the next most shifted line, and so on, that told you something about the correlation function between a zinc impurity and the copper impurities. So you learn something about the microscopic composition of the alloy. And NMR has been a very important tool in alloy physics or metallurgy.
Paolo.
Is there a relation between the nearsightedness and the nodal surface of the main body will function?
And yes, there's just one word I must say it once again, please.
If there is any relation between the nearsightedness and the nodal surface of the many body will function?
Well, it's not a question I've asked myself before, and I'll let you make the choice. If you want to wait 10 or 15 minutes, I can probably give you a fairly reliable answer. If you only want to wait 1 or 2 minutes, it's more or less reliable. What's your choice?
Only on me.
1 minute? Okay.
No.
Probably no.
Maybe we can ask the question again tomorrow night.
No, I'm not going to think about this all night.
Oh.
Let's try this. wave functions are not nearsighted, right? Because if you make a perturbation very distant from, if you change the boundary condition very distant from the place where you observe the wave function, it changes a lot, right?
Absolutely.
This is not an answer, of course, but I don't know.
You reach the same conclusion, I think.
But maybe the place where a wave function, no, the nodes would change. For one electron, they would change all the time, right? Because
Absolutely.
yeah.
The nodes is a very interesting fact. If you introduce a single impurity, let's take one dimension. In fact, it's most pronounced in one dimension. Take a single impurity, and you ask at the point at the origin, and you ask, I look at this one-dimensional wave function. How far away from the origin can I still discover that I've put this impurity in there? The answer is arbitrarily far away. Not nearsighted. Not nearsighted. If you ask for the density of the electrons, starting from the bottom, from the lowest energy electron up to some finite level, it's nearsighted. The density changes of the different electronic occupied states in the density changes interfere with one another, and as a result, what for one wave function is an infinitely far effect of the density. For a dense group of such states, it tapers off. It's different, tapers off differently for insulators than for metals, but it tapers off. It's finite.
So this different behavior between metals and insulators, so this is something I wanted to ask you. I kind of understood that you are suggesting that nearsightedness is more effective in metals than it is in insulators. This is what you said?
That's a very complicated question. So I'm
actually, it was not the question.
1 minute.
No, it was not the question. It was just the question was coming next, but you probably got what the question was going to be.
Well, let me make a statement that may answer your question, or may perhaps at least come somewhere in the vicinity of answering your question. If I introduce a perturbation into a model insulator, filled band, let's say just the lowest band filled, but no interaction between the electrons. If I introduce a perturbation at the origin again, and I ask what is the effect on the density, it falls off exponentially to the effect without the impurity. If you do the same thing for a metal, it falls off in this Friedel manner it falls off in one dimension as 1 over the distance instead of exponentially as 1 over the distance, and it oscillates, as you will know. So that's my answer. See, they're very different, and how you call that, is it more or less nearsighted? You
And
can
this-
make that clear. You can
And
say
this has to do with the decay of the density matrix away from the diagonal. Is this?
No.
And the range of Vanier functions. It has nothing to do.
range
with
of one functions, yes.
But the range of the Vanier function is the decay of the density matrix away from the diagonal, right? When rho of R and R prime, when R and R prime, when the distance between R and R prime grows large, then the decay of the density matrix is related to the behavior of, to the asymptotic behavior of one A function. Or am I wrong?
Well, as you know, one can think about certain question in different ways. I won't say that you're wrong. It's not the way I think about it.
Because you are polite.
Actually, you know, you say I'm polite. I actually have a certificate of politeness. I once took a short plane ride on the East Coast, and as I stepped out, the stewardesses were standing there, and I noticed one of them is holding clearly a bottle wrapped in a nice clean towel. Said, "One moment, sir." We had a bottle of wine left, and we, the stewardesses, said, "We'll give this to the most polite passenger," and I got it.
Great! Congratulations. You are polite and lucky.
All right, maybe it's
Okay.
enough for the night.
Okay.
All right.
I'll give you
So
another
I'll
one.
see you tomorrow, and I'll come with a film, and it's going to be different.
Thank you, Walter.
The revised schedules are here, so I don't know if maybe we want to tell people. We have schedules for the revised schedules. Do you want to pick one up before you leave? Yeah, that's fine. Yeah.